Hi, everyone. I'm Marcin Yumer. I lead the San Francisco office research team at ATG. And in this session, I will talk about the data sets and metrics for self-driving cars. We will give you an overview of self-driving car data sets, starting with Kitty and following up with the most recently introduced ones. We will also touch on metrics and benchmarking, specifically for self-driving car related tasks. We will also show you a little bit of the data sets that are related to HD mapping and localization. Kitty was the first public data set intended for the application of vision in robotics and specifically autonomous driving. The data was captured by driving around in rural areas and highways. It consists of an hour-and-a-half data from multiple cameras, a Velodyne 3D LiDAR, and accurate localization data estimated from GPS and IMU. Importantly, it provides accurate sensor calibration between the cameras, Velodyne to camera, and GPS IMU to Velodyne. Such a collection of sensor data enabled research on many canonical tasks in vision and robotics, including stereo matching and optical flow, 3D visual geometry and SLAM, and 3D object detection. It has been the key to progress in self-driving car technology research for almost a decade. Citiscapes dataset was specifically targeted for the task of semantic understanding of images in the context of self-driving. The goal was to provide a much wider range of highly complex inner city street scenes that significantly exceeds previous efforts in terms of size, annotation richness, and more importantly, regarding scene complexity and variability. The data was collected in 50 cities covering spring, summer, and fall, although not in adverse weather. The data included camera images, vehicle odometry, and GPS tracks. High quality pixel level label is provided for about 5,000 images and coarse annotations for 20,000 or more images, which is the most unique aspect of this data set. Comma AI released a data set of highway driving, which consists of 7.5 hours of driving videos along with vehicle data such as steering angle and speed. The goal of the data set was stated to train models that can generate control commands for self-driving vehicle from the camera feeds. Furthermore, it is used to predict images for the next several images given the previous actions and the previous images in terms of a forecasting task. The deep drive dataset consists of 100,000 videos of driving that are crowdsourced by tens of thousands of drivers. It covers 4 different cities, has balanced day and night data, and extreme weather conditions such as snow and rain. The data includes camera images, IMU, and GPS, but lacks 3D sensors. For each video, a single frame is annotated for image tasks. The annotation includes 6 weather conditions, scene types such as highway, parking gas station, and time of day. Furthermore, drivable area and lane markings and a few categories of objects are also labeled in the images. A subset of the videos have also multiple object tracking labels. ATG4D is a very large scale data set of challenging driving scenarios in multiple cities in North America. It is a unique data set in that it's composed of manually selected safety critical situations. So very challenging scenarios for self-driving. The data includes LiDAR point cloud, images from several cameras, pose, and other vehicle states. In each LiDAR and image frame, all the visible vehicles, pedestrians, and bicyclists are labeled using 2D and 3D bounding boxes. Also, each object has a unique identifier that allows tracking objects throughout the entire sequence. The ApolloScape dataset contains LiDAR point clouds, camera images, accurate IMU, GPS tracks, and the annotations include semantic segmentation, instance segmentation, lane markings, survey-grade 3D point cloud maps. The nuScenes dataset that was recently collected and released is a sensor suite that covers 360 degrees around the vehicle. This dataset is the first AV dataset that includes radar data in addition to the cameras and LiDARs. Similar to ATG4D, this dataset provides 3D bounding box tracks for the visible objects in the scene, which makes it useful for 3D detection and prediction tasks. It also includes semantic map information, providing strong priors for many tasks. The route of the SDV is also included, which can be used for motion planning tasks. About 1,000 scenes in this dataset is manually selected to include high traffic density, rare classes, dangerous situations, and diverse maneuvers. A textual caption is also provided for each scene. Similarly, Argoverse dataset contains 360-degree images around the camera from 7 cameras with overlapping field of view, 3D point clouds from LiDAR, and pose information. It also includes HD maps with geometric and semantic metadata such as lane direction, type, and topology, drivable area, and ground height. Which is actually shown to be improving the accuracy of 3D object detection and prediction. In order to create a challenging data set for the actor prediction task, this data set consists of mined logs in which vehicles are at intersections, turning, lane changing, or are at dense traffic. Waymo also recently released its data set of driving sequences, which includes about 6.5 hours of LiDAR, camera, and pose information. Similar to the previous data sets, the objects in the scene are labeled using 3D and 2D bounding boxes, including street signs. The data set can be used for detection and motion forecasting tasks. Ford released a data set that was collected by multiple vehicles at the same time. The data was collected throughout the year, yielding to various weather conditions. The data contains a 3D map of the environment generated through an offline mapping software pipeline. Unfortunately, no other annotation is provided alongside this data. Most recently, Audi released an autonomous driving dataset, A2D2, which includes synchronized images and 3D point cloud, as well as other vehicle data. This has multiple cameras and LiDARs on board the vehicle. They provide a full 360-degree coverage surrounding the SDV. A set of non-sequential frames of the dataset has semantic segmentation image and point cloud labels. A smaller set of the dataset also consists of 3D bounding boxes for objects in the field of view. The dataset comes with a large set of unlabeled sequential frames. A distinct feature of this dataset is the license, which permits commercial use subject to terms in the license. Here's a final comparison of the datasets covered so far in terms of especially scale. The ATG 4D dataset, as you can see here, is by far the largest dataset available, with around 6,500 different challenging scenarios that are each for 25 seconds. It has over 30 million 3D labels for object detection. Many of the previously mentioned datasets contain high-quality HD maps, which are queryable and accessible as input in addition to sensor data like LiDAR and camera images. Map data includes information like lane geometry, crosswalks, intersections, bike lanes, traffic signs, and signals. This data is crucial to the performance of perception, which is detection and segmentation, as well as tracking, prediction, and planning, providing strong prior knowledge about how vehicles should behave. Moreover, having a stored map database is also crucial for localization. Unfortunately, map data collection through human annotations is slow and expensive, and learning to build and annotate HD maps are challenging tasks in itself. We will go into the detailed steps of map building and annotation in our dedicated HD maps session, but in the following slides, we'll discuss some key mapping tasks and supporting data sets that are available. A classic problem on the mapping side is localization, where the vehicle must use map information and visual cues to understand where itself is compared to the map. Some of the key tasks for constructing maps include lane detection, traffic sign detection, traffic light detection, and construction zone detection. Lane detection is perhaps the most common and most intuitive task. We want to learn to detect the lane markings, which allow us to construct the map topology in the software. Lane detection is also necessary for localization as well as downstream planning tasks. An associated problem in traffic sign detection is understanding and following traffic signs that are critical for navigation and safe driving. A big challenge with the traffic signs is their diversity across geographic regions and the variance in shape and color. An important sub-problem here is traffic light detection. They are an important part of the intersections, which are very complicated scenarios that a self-driving car must master to be able to drive throughout a given urban scenario. We also want to mention construction zones, right? These are important because they temporarily alter the map. When we know that this is an important area that research needs to focus, we also want to mention here that to our knowledge right now, at the moment, there are no public data sets that explicitly deal with construction zones for self-driving cars. We have recently introduced PIT30M, a data set for large-scale localization tailored for self-driving applications. We were motivated by a lack of public localization benchmarks that are large-scale, diverse, and provide accurate ground truth localization. We collected PIT30M with over 1,300 trips over 14 months and include over 30 million images and LiDAR readings. We also carry a consumer-grade GPS in this data set that we use to study localization bootstrapping. To learn more about PIT30M, please check out our localization part of the tutorial that will come in the next couple hours. Here we talk about some common lane detection data sets. TuSimple, for instance, released an initial data set with 7,000 snippets on multi-lane highway roads. Since then, 2 large-scale lane detection data sets have been released. CU lane contains over 130,000 frames throughout driving in Beijing and additionally annotates lane markings that have been occluded or faded. The Berkeley Deep Drive dataset also consists over 100,000 sequences annotating lane markings with 8 categories and additionally include drivable area annotations. We note that the other multimodal datasets such as nuScenes, Argoverse, and Lyft contain map APIs that can be used for mapping tasks, but don't contain leaderboards and to our knowledge aren't currently widely used for this task. The biggest public dataset for traffic sign detection is the Mapillary traffic sign dataset at the moment, containing over 100,000 street level images spanning all over the world. There are 300 total traffic sign classes representing a comprehensive taxonomy and contains additional attributes per sign, such as if it's occluded or out of frame. The data collected under a variety of weather and lighting conditions, such as sun, rain, snow, dawn, daylight, and nighttime as well. We would like to also mention the interesting sub-problem of traffic light detection, which is detecting where it is and what state the light is in. There aren't too many public datasets in this space besides the LISA traffic light dataset, which contains about 43,000 frames of traffic lights in various conditions driving in San Diego. We will now switch our focus to talk about metrics and benchmarks. The goal of self-driving vehicle is to provide an automated way to drive to a location given a starting point and a requested destination. In the previous parts of the tutorial, we learned how different parts of the autonomy stack help to achieve this goal. One way to measure performance of a self-driving stack is by looking at individual components, right? You can look at the performance of the object detector, for instance, if that's part of the self-driving car stack. In the following, we will look at some of these main tasks and discuss how to measure the performance of each one of them. The detection task generates a set of bounding boxes for detected objects of each class. Each bounding box has a confidence score that indicates the certainty of the model. The generated bounding boxes are filtered using a confidence threshold, and the metrics are computed on the set of remaining bounding boxes. Each bounding box of a specific object class is then associated to a ground truth label of the same class if they have enough overlap. And there are different thresholds that different methods use here. This is generally measured through intersection over union. If such an association is possible, the predicted bounding box is considered a true positive, right? If a detected bounding box is not matched by a label, it's considered a false positive. Similarly, a bounding box label with no associated detection is considered a false negative. Bounding boxes with low confidence score that do not have enough overlap with a ground truth object is called true negative. Two main metrics that are calculated using these definitions are precision and recall. Precision is defined as the number of true positives over the sum of true positives and false positives. It indicates how much of the detected objects are really relevant. Recall is defined as the number of true positives over the sum of true positives and false negatives, indicating how the detection model is able to find the relevant objects. To obtain a combined metric, the harmonic mean of the precision and recall is normally used, which is called the F1 score. Note that by setting the confidence score threshold to different levels, these metrics will change. Using a high confidence threshold only leaves the easily detected objects that the model is certain about, and then will yield a higher precision, but will yield a low recall. Similarly, setting the threshold to a low value will pass uncertain detections to the metric, and hence yield a lower precision and higher recall. Therefore, a popular practice is to look at the precision recall curve that is generated by different confidence thresholds. The area under the curve, also known as average precision, can be used to compare two detection models. When multiple classes of objects are in the task, the mean of the average precision over the classes is used as the final metric if there is one metric to look at to compare different models. In semantic image understanding, there are two important tasks of semantic segmentation and instance segmentation. The former focuses on segmenting amorphous image regions, which share similar texture, material, or class in general, right? Such as grass, sky, road, whereas the latter focuses on segmenting countable objects, such as people, bicyclists, and cars. Let's start with semantic segmentation. The model generates a prediction mask over an image for each semantic class. We can simply use the intersection over union between the ground truth mask and the predicted mask as a metric for this task. Similarly, when multiple classes are present, we can use the mean intersection over union over the classes in order to take into account the imbalance between the number of pixels in the semantic classes. The IOU can be weighted by the frequency of that class, yielding the frequency weighted IOU. For evaluating instance segmentation, we follow the same metrics as introduced in the detection part. Similarly, because these are looking at instances rather than the entire image semantic pixel level segmentations. Now let's look at how we can evaluate the motion planning part of the autonomy stack. The most important aspect of self-driving is safety. For motion planning, it means that the SDV should not collide with any object in the environment. One way to measure such a metric is in an open loop fashion is to obtain the rate of collision of the ground truth object labels over the planning horizon. This can be computed by considering the planned trajectory at each iteration. Another level of measuring safety is to measure how the SDV moves when in close vicinity of a specific class of actor. For example, a high-speed maneuver close to a vulnerable road user, such as a pedestrian, signifies a non-cautious behavior. Another aspect of driving is respecting the traffic rules. The violation of some of the driving rules can be verified using the executed trajectory of the self-driving car and the map information. For example, each road or lane is associated with a speed limit or direction of travel. An example metric that can look at this type of traffic violation is the rate of violating a solid boundary line. Some of the other rules depend on the dynamic state of the environment. For example, in the case of a red traffic light, the SDV should come to a stop at the stop line before the intersection. We can compute, for example, the rate of violating such a behavior to measure the interaction with traffic lights. Similarly, comfort is an important aspect of the ride. In a self-driving vehicle, smooth acceleration and avoiding hard brakes can highly affect the experience of the riders. To measure comfort, the rate of change in forward acceleration of the vehicle can be used, which is also known as motion jerk. Furthermore, lateral acceleration can indicate how fast the vehicle moves at a curvy lane, such as a turn. Turning at a high speed is very unpleasant for the riders. Other comfort measures, such as constantly weaving motion, should also be considered as comfort metrics. The SDV also needs to remain on the prescribed route and make progress towards the destination. These metrics can be easily measured using the map, road, and driving data. One way to evaluate the motion planning decision making is to compare the SDV trajectory and the actions with a trained driver. For example, at each planning iteration, we can measure how close the planner planned trajectory is to the actual trajectory that the human driver took. And we can use this, use an L2 norm to compute the difference here. We can also compare the self-driving car and the actual driver's path based on the path and the velocity profile. For example, the SDV might be programmed to be more cautious than humans and yield to a crossing pedestrian, even though that was not necessarily a necessary action to do so. But it is still on the same path as the human driver, right? In general, the SDV just acted much more cautiously. This allows considering the difference in behavioral decisions in some of these scenarios that the SDV can be facing in the real world. To conclude, we went over several data sets that are publicly available for research in self-driving cars. And as we have discussed, the data sets vary in terms of their size and scale, and some of the tasks that are available that you can benchmark through these data sets. They also contain a diverse set of sensor suites and configurations. Also, many of the data sets are aimed at multiple tasks in self-driving, whereas others are focused on a more specific one. And then we also introduced some of the metrics that are used to evaluate and benchmark specific self-driving car tasks. Thank you for joining us in this session, and we will see you in the next session soon.